So, fine. Yeah. So, we'll start with the two-way fixed effect. So, recall what we have done. We have control for unobserved heterogeneity at the cross-sectional level. However, we can think of a possible scenario where unobserved heterogeneity can be there in terms of time also, right? What are the possible explanations that you can think of? One way to think about it, that there could be macro shocks which occurs and I don't have any control for it, but the macro shocks affects all the units in the panel, given it's a macro shock, exactly in the same fashion. So therefore, I need to control for unobserved heterogeneity at the time level. Clear? So if I have the yearly data, I need to control unobserved heterogeneity at year level. If I have quarterly data, at the quarter level. If I have monthly data, at the monthly level. What is the easiest way I can do about it? Note what we have done so far, that we include the fixed effect at the individual level to get rid of individual time invariant unobserved heterogeneity. My then issue is that if the unobserved shock that affect all individuals in particular time period, if they are correlated now with the regressor. What do I mean by that, right? What do I mean by that? Now think of phi t is nothing but phi subscript t. Phi t is nothing but those unobserved shocks. So you already have covariance of your Ci and Xit is not equal to 0. Now you also have covariance of phi t and Xit is not equal to 0. So you have unobserved heterogeneity not only at the cross-sectional level, but as well as at the time of observation. So note, I can think of simply that I can include dummies for each one of the time period, and then I run a fixed effect regression, right? So I introduce a dummy for each one of for each year of the observation. So for example, if I have data for 3 time periods, I am going to include 2 dummies because one would act as the base category. So all I want to do, that I want to augment my fixed effect regression by inclusion of t minus 1 time period dummies, where t is nothing but the number of years of observation that you have in your panel. So given that, all I did is the same regression, but I am now running with I dot interview year, because interview year was the time dimension in the NLSY dataset. Again, if you observe, college graduate is getting dropped because it's a fixed effect regression. However, I have the interview year dummies, which is 1972 and 1973. None of them are significant. You can actually test the significance of time shocks or this aggregate shock, what we call more in terms of panel data literature, by doing an F test in terms of the time dummies. And if they are significant, then you can claim that you need time effects in your model. Otherwise, you don't include the time effects in your model. Okay. So what I do basically, what I want to think of that I do a different way. I can think of getting rid of fixed effect model or unobserved heterogeneity. Of course I can, because I can do things like, instead of taking xit minus xi bar and yit minus yi bar to get rid of my CIs, right? I can take a first difference transformation. So remember, when I do the fixed effect model, I run a regression of yi tilde on xi tilde, right? Where yi tilde is nothing but yit minus yi bar, xit tilde is xit minus xi bar, right? So I then get rid of unobserved heterogeneity by doing this within transformation. However, I can think of that I want to run the model on yit minus 1 and xit minus xit minus 1. That way also I can get rid of my CI. So in this particular case, I can think of running a regression of delta YIT, where delta YIT is equal to YIT minus YIT minus 1 on delta XIT, which is XIT minus XIT minus 1, and call this as nothing but beta hat FD, simply because FD defines that it is a first difference estimator instead of FE, which is my fixed effect estimator. So basically, I want to think of that what does the beta hat FD then would imply in terms of interpretation. I can think of that is nothing but association of individual specific one period change in the regressor or in the explanatory variable and the dependent variable. Clear? Because my dependent variable is YIT minus YIT minus 1. My independent variable or explanatory variables are the set of XIT minus XIT minus 1. So I can do that, and then I lose the one observation, right? Because I'm taking the first difference, okay? So given I am taking the first difference, I'm going to lose one observation, and here I'm going to then regress on log wedge difference on the experience difference. Clear? Fine. So remember, I'm going to do that. So first difference estimator, YIT minus YIT minus 1 is going to be equal to XIT minus XIT minus 1, beta plus UIT minus UIT minus 1. So what I now need for my consistency, look at the error term. So the error term is UIT minus UIT minus 1, and then for the consistency I need expected value of this guy conditional on XIT and XIT minus 1 must be equal to 0. Right? It is weaker than the strong exogeneity assumption because the strong exogeneity needs UIT conditional on entire set of time, entire set of explanatory variable should be equal to 0. So it is a little weaker assumption that we need in case of first difference estimator. Note, when t is equal to 2, the FD, beta hat FD is going to be identical with beta hat FE, because the FE is nothing but only one period mean, right? And the one period mean of YIT minus one period mean is nothing but the first difference of YIT on YT and YIT minus 1. If t is greater than 0, greater than 2, I'm sorry. Then beta hat FD is going to be different from beta hat FE, and it will turn out to be inefficient or less efficient compared to your beta hat FE, and UIT is UIT if I assume that it is independently and identically distributed. Clear? Fine. So note, if someone asks you that does your error suffers from serial correlation either in the estimation of FE and in the estimation of, or first order serial correlation in the estimation of FE or in the estimation of FD, then the first order serial correlation question, which is one of my very traditional 2 marks question in applied econometrics at the undergraduate or at the masters, and always most of the time 90% of the students used to get a 0. So I start increasing the marks from 2 to 10 for a one line answer so that I can give them zeros. So given that, why? Because it's a tautology. Because note, what is the error? The error is nothing but UIT minus UIT minus 1, right? What is the coefficient of UIT minus 1? Minus 1. So automatically AR1 would be valid because by construction the error is UIT minus UIT minus 1. Clear? Fine. So you have started with the error, let's say you have started with the error of EIT. You have started with the error of, say, EIT, right? Clear? Where EIT is equal to CI plus UIT. Then you have EIT minus 1, which is CI plus UIT minus 1. Then your error is EIT minus EIT minus 1, which is nothing but UIT minus UIT minus 1, right? Minus 1. So note, this is nothing but equal to minus 1, right? Think of a moving average process. So moving average is nothing but UIT minus UIT minus 1. If you do not have the I dimension over here, then your moving average error is UT minus UT minus 1. So by construction, your error follows a MA1 process, which is nothing but also invertible, not invertible. Why it is not invertible? Because the coefficient is equal to 1 in absolute value. So recall your AR is not being invertible if the coefficient equal to 1. Your MA is not going to be invertible if the coefficient is also equal to 1. And you need a stationarity. For stationarity, you need they are going to be absolute value of them to be less than 1. So if someone asks you that question, then by tautology, by construction, that the error would follow an AR1 process. Hence, when you have t greater than equal to 2, all you can do is test for the AR2 error, right? Not for AR1 error. And that's the simple logic of any one of these model, like a fixed effect or a first difference estimation. Yeah, fine. So given this, I can then do the regression of D on those guys, and I get the first difference estimator in terms of the experience, which is 0.0516 compared to 0.047, which I got in case of the fixed effect model. Okay. Given this, we'll move to the dynamic panels. Okay, clear? Where was it? Okay. So given what I then want to think of, so I'm again dealing with the panel. I already talked about that one way to get rid of the unobserved heterogeneity is by taking first difference, right? So the first difference eliminates the unobserved heterogeneity, but also on the other way, I can think of the ability of this first differencing is quite powerful when I want to think of the family of estimator that people have introduced in case of dynamic panel model. So note what is a dynamic panel, where I am going to think of YIT depends on YIT minus 1. Clear? So that's the simple dynamic panel structure without inclusion of XIT I can think of, right? So let's think of a model. YIT is equal to alpha I plus rho YIT minus 1 plus UIT. Now write the model for the next period. It would be YIT minus 1. That should be equal to alpha I plus rho YIT minus 2 plus UIT minus 1. Take YIT minus 1. The alpha I goes away, so you get delta YIT. That should be equal to rho delta YIT minus 1 plus delta UIT. Clear? But note, if I start with the original model, I had YIT depending on YIT minus 1. Recall, which you have learned perhaps in your basic econometrics, that when I have the lag dependent variable, then the coefficient associated with the lag dependent variable must be, it doesn't get estimated properly, right? So I need to do something like a GLS. One of the GLS method perhaps you are familiar with, or you have heard at least the method, is Cochrane-Orcutt method, right? So that's like kind of method where I want to, when the errors are serially correlated, I want to get rid of that and get something like a GLS kind of estimator. I'm going to bring that paradigm, and here I want to think of that the inherent structure could be dynamic. Why the inherent structure could be dynamic? For example, that I claim with my wage example, that wage depends on experience, education and unobserved ability, but I can then think of that my wage of today also can depend on the wage that I have earned yesterday. Clear? Simply because there could be an issue of bonus, there could be issue of promotion, there could be different issues. So my wage of today can easily depend on wage of yesterday. And if you think of unemployment in a macro sense, then unemployment of today depends on unemployment of yesterday, and lot of time people say that the unemployment is something like what? Is something like a process which stays as it is, right? So given a shock, unemployment goes like the same way. It does not reduces maybe over the year, but or it takes a long time for unemployment to come back to its mean value, right? So unemployment may not be mean reverting, which is nothing but in the literature or in the macro literature, which I don't know anything almost about it, that is known as hysteresis phenomena, right? Clear? And the same thing you can think of the inflation. Okay. So yes, please.
So in the previous session, you had talked about for dealing this heterogeneity of unobserved thing. We use the fixed effect model is able to overcome it.
Yes, as well as the first difference is able to overcome it.
This is the first time I'm hearing that a first difference model in a microeconometric scenario. So
Yeah.
I'm just looking what is the, why are we taking the first? You mentioned in that model also we are able to account for
Yeah.
unobserved
Yeah.
characteristics. Here also we are able to. Why am I
Clear
doing?
for yeah. So I'll explain. Just hold on to it for maybe 10 minutes. Okay. So I then want to think of that I have a dynamic model where YIT depends on YIT minus 1 plus the set of explanatory variable, unobserved heterogeneity Ci with I runs from 1 to n, t runs from 1 to t. Note what I have assumed. I have assumed the absolute value associated with the YIT minus 1 is less than equal to 1. Otherwise, I would end up with a non-invertible path of YIT or explosive path for YIT. Clear? Remember, econometrics of time series is nothing but based on the difference equation and the differential equation. If you don't understand difference equation and differential equation properly, then don't do time series in my mind. Okay? Just don't do it because you'd talk nonsense at one point of time. So given that, what you want to think of, what happens? Shall I continue?
Yes.
Okay. So the standard panel estimator we have studied are going to be inconsistent. Why? The question is that suppose I have covariance of Ci and Xit is equal to 0. Wales or even random effect estimation is inconsistent. Why? Think of the equation as I said to you for the previous period. So first period I have YIT, next period I have YIT minus 1. Gamma YIT minus 1 replaced by gamma YIT minus 2. XIT transpose beta replaced by XIT minus 1 transpose beta. Ci remains unchanged because this is time invariant. UIT get replaced by UIT minus 1. Look at the problem. Regressor YIT minus 1 is correlated with Ci and hence with the composite error term Ci plus UIT. Because I cannot get rid of the correlation of YIT minus 1 and Ci. And if it is correlated with Ci, then it is automatically going to be correlated with UIT. Clear? Because my composite error term in the original model is Ci plus UIT. You see the logic? Right? So given this, what I then want to think of, can I think of the fixed effect transformation over here. So in terms of fixed effect estimation, what I do, I basically get rid of YIT minus YI bar. Of course, my error goes, my unobserved heterogeneity Ci goes away. I can write that as YIT minus 1 minus YI bar, XIT transpose minus XI bar beta, UIT minus U bar. It removes the unobserved heterogeneity, but still inconsistent. Why it is still inconsistent? Look at the second equation again. YIT minus 1 depends on YIT minus 2 plus UIT minus 1. But YIT minus 1 is serially correlated or correlated with UIT minus 1 as well as this guy UI bar. Therefore, the regressor, which is YIT minus 1 minus YI bar, is correlated with the error term. And hence, consistency I can only achieve when UI bar is very small relative to UIT, which is possible in long panels but not in short panels. So if you have a long panel, T is 30, 40, 50, perhaps you can get rid of it. But if T is equal to 5 or 10, you cannot get rid of it. Clear? So, so that's the problem. So what we try to think of, Nickel is a very famous paper. I think if I recall correctly, it is 1981 Econometrica, and it's the paper title is Nickel bias in case of fixed effect estimator. So given this, what I then try to show you, OLS is inconsistent, random effect model is inconsistent, as well as fixed effect model is inconsistent when you have a dynamic panel setting, right? So given this, or a short panel dynamic panel setting. So what I then want to think of, and to get rid of a remedy for this. One of the remedy is being done by, I think the webcast is absent now. It's going on. Oh. So then given that the dynamic panel, I have then the first estimator is by the Anderson-Xiao estimator. Xiao is actually having a panel data book, which I read from first page to last page, unfortunately. So when I was a PhD student, I think that was the previous, long previous edition, but a fantastic book. Anyway, so the dynamic panel for period T and T minus 1 has been written by the first two equations, YIT and YIT minus 1. I then want to think of that, consider a first difference estimator, YIT minus YIT minus 1, gamma YIT minus 1, YIT minus 2, XIT transpose minus XIT minus 1 transpose beta, and UIT minus UIT minus 1. Clear? With I have T is equal to, now starts from this model, I lose the first observation because I am taking the first difference, right? So it starts with capital 2 or 2 second time period until capital T. So first difference estimator, of course, I have CI here, CI here. By first differencing, I am able to cancel the CI, right? But it is inconsistent. Why? Note YIT minus 1 and YIT minus 2, this guy, is correlated with UIT minus UIT minus 1. Why? Because YIT minus 1, which is here, is correlated with UIT minus 1. Simple logic, right? So given this, what I can do, I can think of Anderson-Xiao is nothing but an instrumental variable estimator. What kind of instrument I can think about it? Note, one way to think about it, that I want to instrument, because this is endogenous, YIT minus 1 and YIT minus 2, that covariance between YIT minus 1 and YIT minus 2 is correlated with UIT minus 1, and that causes the problem. And therefore, I want to think of that proposing some instrument. Why? One of the instrument for YIT minus 1 minus YIT minus 2 could be the lagged values of YIT minus 2. Why? Because that breaks the covariance between YIT minus 1 and YIT minus 2 and UIT minus 1, that covariance was not equal to 0. But if I use YIT minus 2 as an instrument for YIT minus 1 and minus YIT minus 2, that could be a good instrument. Why? Because this is not going to be correlated with the error term and correlated with the endogenous variable. Or I can think of do it a little bit more. So one other instrument instead of YIT minus 2 could be YIT minus 2 minus YIT minus 3. Similarly, I can use YIT minus 3 itself. I can also use YIT minus 3 minus yit minus 4, provided I have the data. I can also use yit minus 4. So note my set of instrument is gradually increasing over the time, right? Clear? And hence what I can then end up with, I actually in my model need one instrument for yit minus 1 minus yit minus 2. But I can end up with multiple instrument. When I end up with multiple instrument, what I call the system is nothing but a over-identified system. A just identified system would be nothing but when you have one instrument for one endogenous variable, and hence I can do something like a test for over-identification if I use more instrument for one endogenous variable, and I can end up with that. Clear? Fine? Okay. So given this, what I then want to think of, I estimate this in terms of the stator. That is my equation. I do the first difference transformation, Anderson-Hisao estimator, instrument for log wi t minus 1, log wi t minus 2, with I am instrumenting now that with t minus 2 and t minus 3, and that's how you are writing that command in terms of FD, because this FD would tells data that you need Anderson-Hisao estimator. And or I can simply do IV regress to SLS on this guy, and then where d log wedge lag 1 is being instrumented by d log wedge lag 2. Clear? And then I have d dot experience. Fine? Okay? So that's what I am doing over this stage. Note, this is a 2SLS. Why? Because first stage I would, it is a 2SLS simply because in the first stage I'll regress this on this guy, get the predicted value, and in my next stage I am, instead of this guy, I'm going to use the predicted value, and hence that's nothing but my two-stage least squares model. Clear? Fine. So given this is basically the first difference estimator. You have observation and everything, and then look, I have the d log wedge being regressed on log wedge LD. That means the first difference, or the LD implies that yit minus 2 minus yit minus 3. That's the coefficient, and experience also is being measured appropriately. Recall what I started with. I said there is nothing like Gita or Upanishad being written that I have to use yit minus 2, I have to use yit minus 2 minus yit minus 3 as the instrument. So I want to use the maximum set of instrument is possible. Why? Because that's what the Arolano and Bond proposes. Use the set of instrument as long as your orthogonality condition is being made. What is the orthogonality condition is being made? That lagged of those guys with lagged of that error term must be, or the covariance between the two would be equal to 0. So you can use xit minus j transpose uit minus j as long that's equal to 0. And it is more efficient simply because you are exploiting the variance that can come by imposing the additional moment restriction. So note, what it does, I can use the instrument for yit minus 1 minus yit minus 2 by both yit minus 2, yit minus 3. I can also use yit minus 2 minus yit minus 3. So for one guy, I can end up with 3 instrument over here, and hence if I do a over identification test, it would be distributed with 2 degrees of freedom, because you need 1, you have used 3 minus 1 is equal to 2, and that's your over identification test. The instrument applicable to each time period can differ. For instance, later the time period, I can use more additional lags, right? So I can use yit minus 3, yit minus 4 goes up to yit minus capital T, right? And I can also use their successive first differences as the instrument over here. The number of instrument available, and that's my point, is highest for the dependent variable observed at time t closest to the final time period. Recall, I call that as t minus capital T, right? And the model is over identified, and therefore I do something like generalized method of moment estimator by imposing this additional orthogonality condition for each one of the time period. Okay, so given this, a class of estimator that derives sample moment condition, it's like automatically comes to me. So that's what I said, we want to exploit the moment condition from population moment condition to generate the parameter. What are the population moments, right? The first order moment is mean, the second order moment is variance, the third order is skewness, kurtosis, and goes on and so forth, right? People are in general concerned about mean and the variance. In one of my paper in GRSS, we try to think of that actually that skewness is equally important, rather as well as the kurtosis is important for a distribution of a variable like inflation. Anyway, so method of moment estimator of population mean, everybody knows that it is nothing but that sample average, right? And then example of OLS estimator, think of this as your model. Expectation of u conditional on x is equal to 0. So expectation of u xu is nothing but expectation conditional on x, xu conditional on x, and then this is law of iterated expectation, and it becomes 0, right? What is the sample moment moment condition corresponding to expectation of xu is equal to 0, that you can find out given what I have shown over here. So note the OLS estimator, I have the population moment condition. That corresponding sample moment condition is nothing but the deviation of yi from the xi beta times the xi. The sum of them or the average of them is nothing but equal to 0. Recall, yi minus xi beta is what? Is your residual. What do you need is expectation of xi and the residual in a population context equal to 0. What is the sample counterpart of it? Is nothing but the average of that is going to be equal to 0, and that's what it is. Clear? And hence, given this, MM estimated is nothing but summation of xi transpose xi inverse xi transpose xi, which we are writing as beta hat is equal to x transpose x inverse x transpose y. So note the similarly the IV estimator would be what? Z is an instrument, so I replace the x by the z and I get nothing but an IV estimator. What is the assumption I have here is expected value of z and u is going to be, or the covariance between z and u is going to be equal to 0. Instruments z are correlated with x but not with the error term. Clear? Fine. Shall I move? Too much? With the gear? Because I looked at the watch. It's 12:30. Any questions so far? Yes, please. You'll fall down. Sit down.
Sir, you have mentioned, suppose a case when t is less than n, that time we can use GMM. So now my question is, if in case n is greater than, t is greater than n,
then we don't use GMM.
Sir, why?
We don't, because the problem is that GMM, all asymptotics goes in terms of n. So if n is not sufficiently large, we don't use the GMM. So what you can do over there, you can run the each cross-sectional estimator and then take the averages, which is nothing but known as mean group estimator. Okay? Fine. So for each one of them, you get beta hat I for each one of them, right? And then beta average would be nothing but beta bar. Your variance covariance matrix would be expected value of beta hat I minus beta bar transpose beta hat I minus beta bar, and that's nothing but your mean group estimator. Okay? Clear?
Thank you, sir.
Yeah, so that's how you want to deal with macroeconometric panel, where you have large T but small n. Clear? So T is sufficiently large compared to your N.
Sir,
Here, yes. No, go ahead.
so sir, is there any decision rule when to use GMM?
Oh, of course, because your N should be sufficiently larger than T. So if your N is 1000, and so you will observe that GMM is being used when you deal with microeconometric panel, where you have large cross section of firms or individual and very small time period. The other kind of estimator, the mean group or the pool mean group or whatever you call it, they are being used when you have sufficiently large T compared to N. So in a growth empirics literature, you will observe that the pool mean group or the mean group is being estimated more than this. You can have a scenario where N is equal to almost T. I would prefer still to use mean group rather than using the GMM. Okay. So given this, I then want to continue. So note, suppose we have more instrument than the endogenous variable, then I can think of that the system is over-identified. So we may not be able to satisfy all moment condition. So we want to minimize the magnitude of the vector of expected value of Z and U, which is nothing but the covariance of Z and U. So GMM weights the moment appropriately. So I solve the problem for an optimal beta. The 2SLS estimator, which is a subclass of the GMM estimator. If you recall your first day, we have exactly the same notation, that X transpose PZ, X inverse X transpose PZY, where recall was your PZ and Px was nothing, Pz was nothing but the projection matrix, because I regress the X on the Z, I get the what? The predicted value, and I use the predicted value of the X in my second stage regressor. So in case of beta hat GMM, that is equal to beta hat 2SLS, but when I contrast this IB estimator to the just identified case, note I do not have this, that X transpose PZ X inverse X transpose PZY. I just have Z transpose X inverse Z Y, okay, because I do not have more variables than I need as my instrument when I do not have a over identified system. Okay, so what we call, I think you have, if you recall your econometrics a little bit, then the first estimator is the 2SLS, and the next estimator is nothing but what we call, or what we used to call in the literature as indirect least squares, right? So I hope you recall the term as indirect least squares. So indirect least squares belong here and the 2SLS belongs there. Clear? Fine? Okay. So note, this is why, or this is how we think of Arellano and Bond, that instrumental variable estimation of the first difference transformation with T is equal to running from 2 to capital T, because I lose the first observation. More efficient because I am using, or I am able to use additional lag of the dependent variable as instrument. I can use for YIT minus 1 both YIT minus 2 and YIT minus 3. The model is over identified because I have two instruments, YIT minus 2 and YIT minus 3. For YIT minus 1 minus YIT minus 2. So therefore, I have two instruments, one endogenous variable. My degrees of freedom of over identification test would be 2 minus 1, which is equal to 1. Clear? So if I do that xt bond command in Stata, that I claim already that model this as a GMM, that the instrument type would be GMM, IV experience Y, experience is here and experience is here, simply because I do not claim that X's are endogenous over here. So the variable itself acts as an instrument for my explanatory variable. Experience goes as an instrument for experience. However, I am trying to use the GMM type of instrument over here, that log of wage instead of log of wage in place of L dot log of wage. Remember what I have? I can have 2, I can have 3, I can have the difference, I can have any sort of things as long as I have the data set. So recall, I have now time period T is equal to 4. I use what? log of wage lag 3 to 5. I want to get rid of too many instrument problem, hence I use a command known as the collapse. I am instrumenting log wage by lag 3 and 5. Use the command collapse basically to get rid of the too many instrument. I want to model this as a difference equation or the delta log on delta log YIT, delta log wage IT minus 1, and that's what I am doing. Clear? Fine. So given that, note I have the lag as 3 to 5 and it says the number of instrument as 4. Why it is 4? Note 3 to 5 implies what? YIT minus 3, YIT minus 4, YIT minus 5, and then their successive differences. Clear? Fine. So given this, I get the estimates, and basically instrument for the first difference equation, it tells you that whatever instrument I am using, recall that I said already that experience would act as an instrument for experience, and it says that separate instrument for each period unless collapsed, right? And here it clearly says L3.5 dot log wage is being collapsed. Okay. So we can basically do the panel in terms of Alorano and Bond original paper, sample of 140 UK firms surveyed annually between 1976 to 84. The model forms employment N using a partial adjustment model to reflect the cost of hiring and firing with 2 lags of employment. That's the original paper. It's in Review of Economic Studies, 1999. You can actually download the original Alorano Bond data set by simply using command web use abdata.7. Clear? And the data set indexes observation by firm identifier, which is ID, and then the year. This is their model. Recall that it depends on not only lag NIT minus 1 as well as employment of T minus 2. The variable N is the firm employment. Control includes current and lagged values of wage level, capital stock, sectoral output as a proxy for demand shock, basically. Okay. So all I then want to think of that, consider first the OLS regression model, right? So I am using OLS, I am using the lag of the employment, lag of the wage, lag of the capital, and lag of those demand shocks. Okay, along with YR star, that means I am including the aggregate shock or the ER dummy in the model. Yes. I did not decide. Alorano and Bond decided. Clear? Because it comes from the partial adjustment, and they think that within 2 periods employment would be corrected or comes back to the. You can. That. No, you can. And always you can think of, I include the higher order depending on my number of observation. Remember that you are using more lags, you are losing observation. So 76 to 84, you are using 2 lags, right? And you can check whether the coefficient associated with your lag is significantly different from 0 or not. And then you start reducing the number of lags. Clear? Fine. So I can start with 4, then check the coefficient associated with 4, not significantly different 0, I come back to 3. 3 is not significantly different from 0, I come back to 2. Okay? Fine. So that's my original model. So note what are the problems. First, the coefficient of the first lag is 1.04, the second lag is minus 0.076, sum of the two is less than 1. So recall for the AR model with an AR2 type of structure, mod of rho 1 plus rho 2 must be less than 1. That's not a problem. But recall here, it includes the lag dependent variable, right? Which is going to be a major problem. Okay. So, and the lag dependent variable would be correlated with your error term. That's what we are talking about so far again and again. The problem with OLS estimate is exactly what I said, that NIT minus 1 is positively correlated with unobserved error term, and therefore there would be a bias of estimated value of gamma 1 in the OLS estimator. Now, suppose if I use a fixed effect estimator, can it get rid of that problem? If you recall what we did previously, we said that still it would produce the biased estimate, which we call as the nickel bias. Recall that. So then I want to think of this is my fixed effect model. At least the coefficient is 0.73 and 0.13. Sum of the two is 0.60. Therefore, it is less than equal to 1. So given this, again, the regressor is still serially correlated. Recall what we have talked in terms of the presence of lag dependent variable previously. If I do the instrument, that delta NIT minus 1 with NIT minus 2, I can of course do something like an Anderson-Hisao type of estimator. I have shown you how to do it previously. Recall what I am doing over here. I am using these year dummies 79, 80, 81, 82, 83, right? 84 is my base category. Because of the first difference, I lose one observation. I have two lags in the model, I lose two more, and hence I can have available observation from 79 to 84, but 84 acts as my base year dummy variable. And that's basically my estimator if I apply the Anderson-Hisao. And again, I try to think of it that this is not efficient estimator, and hence for efficiency gain, I want to go and do something like an Arolano bond. If you recall, that's what we were doing in terms of the theories. So the Arolano bond, it's a classic way of thinking of the problem. So this is my model in a first difference framework, right? So for when t is equal to 3, you can think of I started with 76, 77, 78 until it goes on. So when it is 78, I'm going to use delta delta ni2 with ni1. If t is equal to 4, I can use now I have ni1, ni2 and so on. If I go to t minus 1, the last time period, I will have then what? ni1, ni2, nit minus 2, right? Clear? Recall in the first case, t is equal to 3, you can use ni1. T is equal to 4, you can use ni1, ni2. T is equal to capital T, you can use up to t minus 2. Is the logic clear, right? So that's how it goes. And then for each one of those guys, expected value of ni1 and your error term, the covariance between the two is equal to 0. And that's one of the moment condition. Next equation gives you two more moment condition. Next equation gives you one more moment condition. And you will end up with this kind of moment condition. Actually, you can calculate how many moment condition you will get. Okay. No level, basically it estimates the GMM in differences in terms of stata. Small does something like a wind miser correction, and IV basically specifies your exogenous regressor. Because recall, I claim that all the other variables are exogenous. If I claim that, then I can think of that they are acting as instrument for themselves, and I don't need to worry about it. Okay. So this is my model. So note, I get my lag values of employment L1 and L2. I have W, L1 and L2, and then K of the 3 time periods, and that's the way I want to think of the results. Right. I'll stop here. It's 15 minutes back. I have 15 minutes, but I think I should stop here. I don't want to start with DID. Clear? Fine. That's okay, right?
They can go to the slides and then can ask questions.
Yeah.
They already have the material.
Yeah.
You can wait here for 10 minutes.
Yeah, I can wait. Because yes, please.
So, in a way, earlier people used to think so that finding the instrumental variable is the biggest problem.
Yeah.
Whereas now with the panel data,
Yeah.
what we can have is
The lagged values used as an instrument.
lagged values.
Yeah.
So that's like by default it comes up.
It comes. If you have a kind of like sufficiently large panel, like at least t is equal to 5
Yeah,
or
but
6
how
or something.
appropriate is this? I mean, see,
That's like, you know,
so
like it
typically
is.
typically the reviewers will ask, or maybe the researchers also will have a problem.
No, yeah.
Wherever the endogeneity is there, how
Right.
to find the instrumental variable? From where
Yes.
do you get the data?
Absolutely. So the way to think about it, that I here the Arolano bond kind of model mainly concerned with the lag dependent variable. And if I understand you correctly, you are thinking of one of those explanatory variable is endogenous. Like one of the x's is endogenous. In when one of the x's is endogenous, you can of course use the lagged x, but that's not a good instrument. So the way to think about it, can I get an instrument outside something which I think can affect the x, but you know, it could be very strongly correlated with y, but would not be correlated with my error term. So think of an example. There was a paper by Mauro Paolo in very early paper in QJ in 1995, and the title of the paper was Corruption and Growth. Okay, so what you observe in case of growth literature, a little corruption is actually good for growth. So does inequality. But then what happens? Corruption increases, growth increases, inequality increases, growth increases. Then it hits a threshold. After that, the growth starts reducing. But corruption could be endogenous in terms of the growth. Right? That corruption can cause growth, growth can cause corruption. What is the instrument? Lagged values of corruption in this context is not a good instrument. So what Mauro Paolo did, he uses something like ethno-linguistic fractionalization as an instrument. What is the idea behind it? If you speak in the same language and in the same dialect, then for you to get involved in the corrupt activity is very strong or very easier. But there is no way you can think of that, you know, this ethno-linguistic fractionalization has anything to do with your error term. Hence, ethno-linguistic fractionalization act as an instrument for your corruption repression. After you control for growth depends on physical capital, human capital, all sorts of things. That's the case. Okay. So a lot of times you need to think of the instrument outside the lag. One of the classic paper is by Lubel, and it is becoming very popular, the instrument. So the way Lubel does, I mean, we have also myself and Yongchol also some idea about it. So the way Lubel works, so your instrument would be xit minus x I bar. So suppose when I is equal to 1, you are going to use xit minus x bar, but excluding I. You got it, right? So from 1 to n, you are using the deviation of x to t minus x bar, but not including I is equal to 1, from 1. Other way which we think of it, that for unit I, you use j to k. For unit 2, you exclude 2, but then use 1 to k excluding 2. And that is your instrument. Now, you may think of that if I have 100 forms, then I would end up with 99 instruments for each one of them. That's too many. What should you do? One way to think about it, construct a principal component and use the principal component over there instead of this. So that's the idea Yongchol and I had, and we have some results. Yeah. Yeah. Yes. At the end of the day, actually fixed effect is bias corrected fixed effect estimator with Bootstrap performs really well. We have a EJ Ward, European Journal of Operational Research, where with simulation we showed actually XT that Arolano bond estimator, be it difference, be it system estimator, their performance is not that good. There are a lot of other estimators we have in the literature in dynamic parallel, and they perform better in terms of our simulation. Any other question? No? Yes, please.
Is there any, is there any situation from, like there is GMM differences and there is system GMM?
Yeah, yeah.
So then, is there any way then we can know where?
No, I mean, a lot of people, I mean, the fashion is to use now system. Because, like after Alolano bond, there is a paper by Bond and Bover, and then Alolano and Bover, I think. So people started using these system GMM with the small sample correction by Wien-Mercer.
So this system GMM is a combination of this difference
And the level. So it is a combination of the level and this difference equation.
then we are end up getting more instruments.
We are end up getting more instrument. A lot of times getting more instrument means exploiting more moment condition, and therefore it becomes more efficient.
So in principal component analysis
Yes.
mentioned,
Yes.
after getting that 99 or 90, however maximum, then we have to run this principal component to categorize and we can select based on maximum eigenvalue.
Yeah, yeah. You can do that and then use that as an instrument for your endogenous
Whichever is
variable.
having maximum eigenvalue.
Absolutely. Absolutely. And generally, it's extremely hard to get an interpretation with the second principal component or third principal component, right? You just cannot explain it. So a lot of time people end up with the only one principal component. But remember, the principal component of categorical variable is quite different than the principal component of the continuous variable. Yes.
So the basic query between fixed effect model and the random effect model.
Yes.
So in your slides, you have mentioned that the fixed effect eliminates individual time invariant unobserved heterogeneity.
Yes.
So that means the meaning of individual time invariant unobserved heterogeneity, meaning that that an individual grows his
So
experience.
25 of
Just to
you,
give an example.
to 25 of you applied for IIT Indore, right? Somebody performed very well simply because his or her ability, which the panel could not observe, is higher than the others.
Yes.
So then ability is unobserved, but it gets reflected in terms of your performance. So hence, if I have 25 candidates, I need to control for their unobserved ability. But as an interview panel, I don't know your ability when I see you.
But the fixed effect model will
Gets rid of that by simply doing something like a transformation. And the transformation is being done by taking your performance, all of your performance, take the averages of the performance, calculate the deviation of the averages of the performance, right, from your original performance, and similarly you do that with your set of explanatory variable.
And in the random effect model, we are not able to control for this.
We do control for unobserved heterogeneity, but in a different way, right? Because it is a GLS. The main advantage, the main difference between the two, whether you are allowing the unobserved heterogeneity to be correlated with your explanatory variable or not. In a fixed effect model, we assume that they are correlated. In a random effect model, we assume they are uncorrelated. So the covariance of unobserved heterogeneity and XIT is equal to 0 in random effect, but is not equal to 0 in the fixed effect model.
But then, sir, the Hausman statistics would be the null hypothesis.
Is the random effect is correct and the fixed effect is the alternative.
Right.
Yeah.
So if we reject the null hypothesis,
That means
fixed effect.
fixed effect is the correct.
Fixed effect will be there even if we don't like be consistent even under the null also.
Yeah.
And you also mentioned about Mundala
Correction.
So is it like an improved version on random effect?
It is definitely an improved version of random effect because you are allowing somehow the correlation, right? And between or the covariance between alpha I and xit, and then that's definitely an improved version. And the advantage of Moonluck over the fixed effect model is that you are able to get the coefficient associated with your time invariant regressor, right? So in the example that we have shown you, you are getting the coefficient associated with college graduate, a dummy. Yeah.
So no slide is written. If we reject the null, then random effect which is more efficient.
Maybe it is a typo.
Typo.
Yeah, we can. 1257.